We can describe the motion of a particle moving along a planar curve using parametric or vector valued functions. And given we're looking at motion problems, the parameter t represents time. So the velocity is obtained by differentiating the position vector with respect to time. And differentiating the velocity with respect to time is the same as obtaining the second derivative of position with respect to time, and that gives us the acceleration. Now if we integrate the velocity vector with respect to time between time t0 and time t, well, that gives you the displacement or the change in position over that interval of time. And from this you can solve for the position. So recall that the instantaneous speed is the magnitude of the instantaneous velocity, which is written as follows. And if you integrate this with respect to time, from time t0 to time t, well, that gives you the total distance the particle has travelled, or the length of the curve from time t0 to time t. And you can recognize this as the arc length integral. And similarly, if you integrate the acceleration with respect to time, that gives you the change in velocity over that time interval. And this will be clear in the following example problems. Given a position vector for a projectile with this parabolic trajectory, derive an equation for the velocity and acceleration. So in this context, the parameter t is time, because we're looking at a motion problem. And differentiating the position with respect to time, we obtain the velocity, and differentiating the velocity with respect to time, we obtain the acceleration. So only the gravitational acceleration is acting downwards at any point, and it has the same magnitude and direction according to this equation. Now for the velocity, the horizontal component is also constant, and at the top of the trajectory, it's going to look something like this. And given that the acceleration is pointing downwards, then this point is a maximum in the trajectory. And then somewhere over here, the velocity is going to look something like this, but the horizontal component always has the same magnitude, in accordance with this equation. Whereas the vertical component can change direction, as we can see. So if we view another velocity vector here, the horizontal component has the same magnitude, but the vertical component has an upwards direction near the initial part of the trajectory. Given the acceleration vector for a projectile, derive an equation for the velocity and position. So the acceleration is the rate of change of the velocity with respect to time, and that's equal minus the gravitational constant in the vertical direction. And now we can separate the variables and integrate both sides while leaving the constants outside the integral. What we get is the velocity vector is equal to some constant in the horizontal direction plus minus g by time, and plus another constant of integration in the vertical direction. And now applying our initial conditions, so equating the horizontal components and the vertical components at time 0, well, what we get is g by 0 plus cy. And therefore the equation for the velocity can be written as follows. And now you can do the same thing to obtain an equation for the position. So the velocity is the rate of change of position with respect to time. And separating the variables and integrating, And applying your initial condition, you'll be able to get an equation for the position as a function of time. The following function describes the motion of a particle along a curve, and we're asked to describe the motion by analyzing the velocity and acceleration vectors at several points along the curve. So differentiating the position with respect to time, we get the velocity. So we can see that this is a parameterization of a circle with a radius of 1. So substituting for t is 0, we get the velocity pointing in a vertical direction. And drawing in the velocity vectors by plugging in the relevant values for t, they look something like this at these points. And now the acceleration can be obtained by differentiating the velocity with respect to time. And plugging in those different values for t, you're going to get the acceleration vectors all pointing to the center. So we call this acceleration as a centripetal acceleration, or center-seeking acceleration that keeps the particle traveling along a circular path.